One more function that can be associated with random variables is the so-called quantile function. Let x be a random variable. The quantile function is the generalized inverse of the cumulative distribution function of x. It is defined as follows. The quantile function evaluated at the point P is the least q for which the CDF evaluated at q is greater or equal to P. In other words, it's the point where the CDF either hits P or jumps above P. Note here that P is a probability, in other words that P is a number between 0 and 1, and that the quantile function is defined only for numbers between 0 and 1. Equivalently, we could have defined the quantile function as follows. The quantile function evaluated at P is the supremum over all Q, where the CDF evaluated at Q is strictly less than P. The basic relationship between cumulative distribution functions and the associated quantile functions is the following. The CDF evaluated at Q is less than or equal to P if and only if Q is less than or equal to the quantile function evaluated at P. In other words, it looks like you can take this fx over here to the other side and then it becomes fx inverse. Now there is not a single way to define quantiles. More accurately, a p-quantile of a random variable is any number q with the property that the CDF evaluated at q, in other words the probability that x is less than or equal to q, is greater or equal to P, and the probability that x is strictly less than q is less than or equal to P. The definition that we take here is the one that selects the smallest p quantile. However, this is not the only definition of quantile, and various software packages will, for example, use slightly different definitions. Note that when the CDF is strictly increasing and continuous, then the quantile function evaluated at P is the unique number q where the CDF evaluated at q is equal to P. In other words, it's then the point q where the CDF hits the level P. Graphically, suppose that we have a CDF shown in black over here, and that P is a number between 0 and 1. In this case, the CDF is strictly increasing and continuous. And if we would like to compute the quantile function at the point P, then it's the point where the CDF hits the level P. In other words, this value here is the quantile function evaluated at the point P. Over here, the CDF has a jump. If we would like to compute the quantile function at the point P over here, it is the first place where the CDF hits or jumps above the level P. In other words, it's this point over here. Remember that a CDF is always right continuous, which means that we always color in the point just after the jump and leave the point just before the jump as an open circle. The 0.5 quantile is called the median of the distribution. It has the property that half the probability mass of a random variable lies below the median. In other words, the probability that x is less than or equal to the median is equal to a half. Similarly, the 0.25 and 0.75 quantiles are called the first and third quartiles. And we can talk about percentiles as well, etc. As we've stated before, the quantile function is only defined on the interval from 0 to 1. You put into the quantile function a probability, and out comes a quantile. This explains the use of the letters P and Q on the previous slide. Now note that whereas the CDF is a right continuous function, the quantile function is a left continuous function. Now graphically, the graph of the quantile function is just a reflection of the graph of the CDF in the line y is equal to x. To see this, first note that the reflection of a point QP in the line y is equal to x is just the point PQ. Now the point QP lies on or below the graph of the CDF if and only if the CDF evaluated at Q is less than or equal to P. By the relationship between CDFs and quantile function, this is the case if and only if Q is less than or equal to the quantile function evaluated at P. And that is the case if and only if the point PQ lies on or above the graph of the quantile function. In other words, a point QP lies on the graph of the CDF if and only if its reflection, the point PQ, lies on the graph of the quantile function. Here are some examples. We have here the CDF of the standard normal distribution. Its values lie between 0 and 1, as we can see. Here is the line y is equal to x. Its reflection is the quantile function associated with the standard normal distribution, and it is only defined for values between 0 and 1. Now, a CDF can also have jumps. You can see here this is a increasing function. It has jumps. It's right continuous. Its reflection, i.e. the associated quantile function, is shown in blue over here, and is a left continuous function. Notice that wherever the CDF has a jump, the quantile function has an associated level bit, whereas where the CDF is level, the quantile function has an associated jump. We've seen that we can get an estimator of the true CDF from a sample of identically distributed data points using the empirical CDF. In the same way, we can obtain an estimator of the quantile function of a distribution from data using sample quantile functions. Recall that the pth quantile of a distribution f is defined to be the least q for which the distribution function is greater or equal to p. The pth sample quantile is defined in the same way. Suppose that we have n data points. Associated with those data points is an empirical distribution function, f hat n. And the sample quantile function is simply the generalized inverse of the empirical CDF. In other words, the sample quantile function evaluated at the point P is the least q where the empirical CDF hits or jumps above the level P.